Cloud. Good morning, sort of, I guess. Technically, still morning, although for many of you, I think it's not morning. But one thing I was thinking about was because a lot of you are in data science, but then I just assumed that you had already taken a term of data science, but that's not necessarily the case, is it? Is anyone just starting the data science program? I can't see a little. Okay. Yeah, I don't know why I didn't clue in. Yeah, so a lot of you have just started. Welcome. I had a class during the orientation, so I didn't. Yeah, and then I've got my biology crew. So they cross-listed this course, and it's like most people are in data science, and then there's my biology crew, and we're just doing our best here. But I think everyone's kind of on the same page. We're just getting started, and if you feel comfortable with R, that's great. But I'm assuming that you haven't had very much experience at all. And in fact, I'm assuming that you've had zero experience, which I know is not really the case, but it's just a nice way to start, okay? And so today I do want to introduce a little bit of R code, just to show you that it can kind of speed things up a little bit. But yeah, so I realized that maybe not everyone has everything set up on their computers, because I saw that there's still some R Markdown, kind of those test Markdown documents that haven't been submitted yet. So if you're still kind of struggling with that, then that's totally fine. Just reach out to me and I'll help you get set up, because that's going to help you in your, especially if you're in the data science program, you'll need to have that all set up. Because Bevan and Joe are gonna ride you guys hard. So, well, and Julian, I don't know, whoever's teaching that. So yeah, that's just something that I realized that I thought, oh, they might just be new. Okay, so, and I know for biology, some of you've used maybe R a little bit, but let's assume, let's just start fresh, okay? So what I wanted to say here, if you haven't submitted your Markdown test document, and need help with it, set up a time with me. And I will help you get set up. Okay. So what happened was, well, today I'm kind of, my nose is so runny today, so I probably shouldn't go to work. So it's probably good that we're online anyways, but I checked the polls and I tried to get us a room, and there is a room, but it's the huge theater. And I saw that only 2 people were planning on coming in person, and potentially 3. And I kind of talked to one of them. Anyways, he said they're okay to go online. So if we can just go online until I get this, well, probably indefinitely. But there might be some kind of review days that might be nice to have the possibility of in person, or I can schedule extra time if we want to. Okay, I also have the in-person lecture Monday, Wednesdays at the same time, and you're welcome to come to that if you want to have kind of the in-person experience with other people there, not just 1 or 2. well, there won't be that many in that class either, but anyways, so you've got options. Just kind of reach out to me and if there's something that you want changed. Okay, so the markdown document is due, but because I'm just trying to get everyone on the same page, just make sure you submit it. Even if it's late, it's fine. I just want everyone to show me that you're up and running. Okay, so just make sure you submit that. Okay, last day, trying to think if there's like any other administrative stuff that I wanted to talk about, but I don't think so. Let's do some quick review. We introduced a lot of concepts, and but today we're going to build on those concepts, and we're going to talk about numerical summary. So we talked about data visualization, right? So visualizing numerical data with histograms. I don't know why I capitalized everything there, but I did, with histograms. Okay, and we talked about things like the shape, the center, the spread, right? And so to describe a distribution, we need to discuss the shape, the center, and the spread. Okay. And the shape, we're going to focus on either if it's normal or non-normal. And we talked about some other different shapes, like it's skewed to the left or skewed to the right, or maybe it's bimodal or even multimodal. But in general, I want us to start classifying things as either normal or non-normal. Normal versus non-normal. Okay. Now, the reason for that is because if we can argue that we have a normal distribution, then there are a lot of things that we can do later on. Okay, so if you've ever heard of a t-test, for example, it assumes that you have an approximately normal distribution, and you can't really use it unless you do, right? So things like that kind of hinge on having a normal distribution. So for our purposes, I just want to separate things as either normal or non-normal. Okay. For the center, this is just an approximate center. Okay, when we're just describing the distribution, we don't have to get all crazy technical. We're just approximating. Approximate center. And same thing with the spread, minimum to the maximum, right? Kind of the range. Don't be confused. If you've taken other math courses, you know that the range is the range of the y values. That's not what we're talking about here. When I say range in terms of a histogram, I actually mean the range from minimum to maximum, right? And so I'm going to follow it up and say, call it the range here, just so you start making that connection. So context is going to be really important here, because sometimes I'll mean the range for the y values, not very often though. But if you've taken calculus, for example, then you know that that's important, but I say range minimum to maximum here, and that's what I mean. So, and you can always clarify with me if you're not sure. So, that's kind of where we got to. So depending on if we have a normal distribution or a non-normal distribution, that's going to dictate the appropriate measures. Now we're going to be talking about numerical measures of center and spread. Okay, so for normal distributions, we're going to have specific numerical measures of center and spread. And for non-normal distributions, we have more appropriate measures of center and spread. So it's all gonna, so the shape is going to dictate the appropriate measure of center and spread. So today what I want to talk about, or start talking about, it didn't get nearly as far as I wanted to in my class yesterday. So this is my second go at it. So I'm usually like a little bit faster because I kind of trim the fat, so to speak. But I didn't get nearly as far as I wanted to, so we'll probably carry it on into next week, but that's fine, because what I want to talk about is our numerical measures of center and spread, right? So kind of more concrete values that we can talk about, right? Instead of just describing the distribution. Okay. I'll call this kind of the end of the review. Not much of a review. Often when we've had a class earlier in the week, I feel like I don't have to spend so much time reviewing because it should be pretty fresh. Whereas when we meet back on Tuesday, then I'll do a bigger review if we need it. Okay, so the shape of the distribution which we're either classifying as normal or non-normal, will dictate the appropriate measures of center and spread. The appropriate measures, numerical measures, let's clarify here, measures of center and spread. Okay. So I do have it in my, the handout that I posted, the chapter 2 handout. And I want to jump there. I'm gonna grab that, pull that in. And what I've decided to do for you guys is kind of focus on using R to do these calculations. I'll show you how to do them by hand, but ultimately in life, you're going to be using software to do these calculations. It's good to be familiar with how you would do it by hand, but my focus is going to be, can you calculate these values using R, right? Or some other software. If you prefer to use Excel, for example, that's fine for the beginning here. Excel does the exact same thing that we do, and it's totally fine. We need to know things like, what is the mean? What is the median? What is the standard deviation or the variance? What is the interquartile range? And so that's what I'm going to develop today, and that's what we're going to talk about today. And then I'm going to show you how to do those. I'm going to focus on the calculations in R, and then in the handout, there are more calculations by hand, and we'll get through those if we have time today, but I think not. Save them for tomorrow. Okay, so depending on if we have a normal or non-normal distribution, our numerical measures of center and spread are going to be, so if I have a normal distribution here, right? So if I have a normal versus non-normal distribution, the appropriate measure of center is going to be the mean. Now, what is the mean, right? And so here, let me shrink this up. Can I kind of have to blow my nose. Yeah, I really shouldn't go to school, so it's probably good. I feel like that's gonna happen a lot this term. Everyone's sick all the time. And usually we would just go and be sick together at school, but that's bad. We're not doing that anymore. It's good. It's good that we're not doing it anymore. So the mean is the average. I use the two interchangeably, okay? And so in statistics, we should be using the term mean. It sounds a little bit better, but everyone should be comfortable using these two interchangeably. Okay, so the mean is the average. And if I gave you a list of numbers, I would expect you to be able to find the average of those numbers, right? What's the average of 4 and 3 and 12 and 19? What would you do? You would add them up, right? And then you would divide by however many there were. So, for example, find the average of 4, 3, 12, and 19, I think I said. Okay. Well, you would do 4 plus 3 plus 12 plus 19. Remember, the notation that we're using is X bar for the mean, specifically the sample mean. Okay. Divided by 4. Okay. So X bar in this case doesn't really matter, but I'll grab my calculator just in case. 4 plus 3 plus 12 plus 19 is 38 divided by 4, puts me at 9.5. So you should be comfortable finding the average or finding the mean. That's not a problem, right? So here, the mean is denoted by X bar. That's the sample mean. So how do we summarize this in notation? Well, if I'm adding up, if these are all my X's, which is typically how we denote them if we're calling it the average of X, right? So then my X has a list of 4, 3, 12, and 19. And if I sum up all my X's, that would be the 38. And then my sample size, remember, is n, lowercase n. Okay. So the mean is the average, and X bar is the sum of the X's over n. Okay. Add up the X's. N is the sample size of X is implied there. Okay, so what we're gonna have is we're gonna have these formulas that do use summation notation. So if that's a little bit rusty, then that's okay, right? I'm gonna focus on using software, but it's good to kind of make the connection between, oh, well, I know how to do this, right? I know to add up all the values and I know to divide by the number of the values, right? And so even when we have kind of weird formulas like this, and they're gonna get weirder, I promise, we can kind of break them down, right? And we can work through them, right? But of course, R or Excel or whatever software you're using, I'm gonna use R with you guys, we'll just do this, okay? I'm trying to remember what the notation for the median is. I feel like it's an X with a little squiggle on top, I think. But so the average, I mean, we talked about it here, but we all have a pretty good understanding of what the average is. Not necessarily the same for the median. Okay, so the median is the central value. The central value of the data. Okay. So what happens is, okay, so to find the median of a set of numbers, I first have to sort them. And typically we sort from smallest to largest. You could be weird and sort from largest to smallest, but I'm going to assume that you're not doing that. I just always sort from smallest to largest. And so here, to find the median, you're going to sort the data from smallest to largest. And then there are fancy ways to find the median, but I use my my patent pending boop, boop, boop method, where I just, because we're going to, if I'm getting you to do it with a small data set, you can just write out, you can sort the data, and then you take your fingers and you boop, 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 because you're trying to find the central value, right? It's not fancy or anything, and there are fancier ways to do it, but they tend to only give you the location of the median, so you would still have to count in and find it. So I just find that the boop, boop, boop method is a little bit easier. Don't worry, the boop, boop, boop method is not real. It's only me. So if you try to Google it, then I don't think anything comes up. But it's what I use. So use the boop, boop, boop method. Has to be 3 boops. To find the central value. Okay. If you land on 1 value, then that is the median. If you land on 2 values at the same time, which totally it happens, then you're going to take the average of those 2 values. And I know that's confusing because we're trying to find the median, but then if we land on 2, we take the average. I don't make up the rules, guys. It's just that, but that's what we've landed on if we're doing it by hand. Okay, so if you land on 1 value, that value is the median. Okay, but if you land on 2 values, the average or the mean of those 2 values, right? But I use them interchangeably. So the average of those 2 values will be the median. Okay. So I've got an example that I want to show you guys kind of what to do. And it's the GDP data that's it's kind of lower in the, here. So we're going to be using these values as our example because the 4 values can only take us so far, right? Finding the central value of 4 values, it doesn't really tell us very much, right? But here we have a small data set that we can still do things with, okay? So the success of companies expanding to developing regions of the world depends in part on the prosperity of the countries in those regions. Here are the World Bank data on the growth in domestic product, so the GDP % per year for the period 2000 to 2004 in countries in Asia, not including Japan, right? We have to specify the population that we're looking at. So our GDP information is listed here. And so these are the data points or the values of X that we are going to look at, okay? So there are 12 points, I think. Let me just confirm. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So first things first, I see that n is 12, right? Maybe that doesn't look like 2 quite there. Okay, so we have a sample size of 12, right? And if I asked you to find the average of these, you can do it. It's just tedious, right? So I'm gonna leave that for R to do, but you can absolutely do that. So to find the median though, that's what I wanna focus on. So let's find the median of these values. I'll say we will use R to find the mean of these values. We absolutely can do it by hand, like I said, but we're gonna focus on using R. And then what I wanna do, so now to find the median, we first need to sort the data from smallest to largest. Okay, so what I like to do is as I go, I cross things off, and then once I've listed them all, I count to make sure that I have 12 again. So it's really just a lot of kind of making sure that I've covered all my bases, right? And so let's go through these. And I see a 2.9, so I'm gonna start here. It's quite a large data set, so well, like for doing it by hand, it's a very, very small, but for writing it out by hand. So I want to make sure that I use my entire page here, just as a heads up. You could sort them like this, so vertically, but for me, I like the visual of horizontally, so then I'm limited by my page. Because I'm on my iPad, I'll be able to copy and paste these values again. And I know that's kind of annoying if you're writing it out, but just kind of maybe save it. And I'll post these notes, obviously, so you'll be able to look back. But it does make me go a little bit faster than writing it by hand, which is good, but just as a heads up. So I've used 2.9, and then I find, I see a 3.2. I think 3.2 is next. I see a 3.9. I see a 4.1, 4.4, 4.6, 4.7, 5.2, 5.4, 6.2, 7.3, and 9.4. Okay. And you know what? I'm gonna maybe bump these over here so that they're not crossed out when I post the notes later. Okay, but so I do cross them off and just make sure, and then now I'm gonna count these just to make sure that I still have 12, because it would change everything, right? If I'm trying to find the central value and I've lost a value, or maybe duplicated a value, that's gonna change stuff. So I don't want that to happen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, phew. Okay, so now, and you can just double check, make sure that they are sorted from smallest to largest, but these are all kind of check-in points that you can or don't have to do, but they definitely help. Make sure you didn't screw anything up. Okay, so to find the median, what I want to do is I'm going to take my two fingers, and I tend to have to do it a couple of times because my it's hard to look at, right? But I take my two fingers and then I count my way in, right? And so to show that, I'm going to boop, 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 keep going, boop, 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 boop. Okay, here, like that. Okay, so what happened is I landed on 4.6 as well as 4.7. So when I boop, 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 kind of had to do it to write it out. But, right, so I land on 4.6 and 4.7. So here, what I do to show that I'm taking the average here, or finding the mean of these two, I circle both values, and then I draw a line down the center to show that that's where the median is, okay? And then I can show that the median is 4.6 plus 4.7 divided by 2, which is 4.65. Okay. Good. Notice what would happen to the median, even if this was, maybe this value, this 9.4, imagine the 9.4 is 94, right? In terms of all the other values, 94 compared to a maximum, kind of a lower maximum of 7.3 is huge, right? So then we would have this outlier, right? And same thing can happen on the lower end, but let's focus, I'm just focusing on the upper end. Okay, and so let's say that this is 94. What would happen to the median? Nothing, right? Because the median doesn't care whether this is 9.4 or 94, right? And so what we say is that the median is robust to outliers. Okay. Whereas if you imagine taking the average of these values as they are, right, versus the average with this value being 94, right, then that average is going to be shifted towards the outlier, okay, whereas the median stays the same. Okay. So consider this scenario where the 9.4 value is changed to 94. To 94. 94 would be an extreme outlier compared to the rest of the data. All right, a value of 94 would be an extreme outlier compared to the rest of the data. Okay, so now I'm just gonna copy this whole chunk here. Copy, paste. Okay, maybe I'll try to keep it nice and tight here. And if I change this to 94, so not 9.4, but 94, right? Notice that the median does not change, right? So we notice the median does not change. Right? So what we say is we say that the median is robust to outliers. Right? For this reason, we say the median is robust. Oops. robust to outliers. Whereas the mean, right? The mean is always pulled in the direction of the outliers, or outlier potentially. Whereas the mean is always pulled towards the outlier. So is always pulled towards outliers in brackets. And maybe I should say the outliers, potentially more than one. Okay. So this is the same as what we saw in a skewed distribution, right? So if I have a skewed distribution that looks like this, right? This is showing me that I have outliers on the upper end. That's why the tail is being pulled in that direction. So outliers on the upper end. Yeah. So for that reason, the median is kind of holding steady here. The median is here, and the mean might be pulled over towards the tail. So we said that last day. We said, okay, well, if you have a skewed distribution, the mean is always pulled in the direction of the tail. Okay, I think we said that. Should have, if I didn't. Okay, so we say that the median is robust to outliers. It can handle those different outliers. Okay, and so and just remember that if you have a skewed distribution, it means that there are outliers in the tail. Okay, okay. So let's scroll back up, and I know it's going to be all laggy here. So we talked about the, oh, it's just catching up here. Ah, come on. There. Okay, so the mean, we've talked about that. We've talked about the median. One other scenario is where you would land on one value. I'll show you that scenario when we talk about the interquartile range. We haven't talked about that yet, right? So we don't know what it is. Standard deviation is the appropriate measure of spread if we have a normal distribution. Now, if you go on into kind of deeper statistics, you'll likely end up using the variance, but for a couple of reasons, it's a little bit easier to talk about the standard deviation, so that's going to be my focus. But the standard deviation is the square root of the variance, and that's it. So I'll show you that connection, and then we're going to talk about the interquartile range. Okay, so and I'm kind of going rogue from those notes that I posted, but all the same information is there. I'm just kind of introducing it in a slightly different order, that's all. And maybe not even. I just didn't really look at the notes that I posted. Same information though. Okay, so the standard deviation of data is a measure of spread, and it's the appropriate measure of spread if we have a normal distribution. Okay. So if we have a normal distribution, the appropriate measure of center, or sorry, of spread, the appropriate measure of spread is the standard deviation or the variance. Okay. The standard deviation is denoted by S. So here, because we are doing these calculations, we are only working with sample information. Okay, and so then we use a lowercase s. And so the standard deviation and maybe I'll say sample standard deviation, just to clarify, is denoted by S, so a lowercase s, whereas the sample variance is S squared. Okay, so that means that if we rewrite the sample standard deviation just as SD and the variance just as var, just as shorthand notation, what does that mean? It means that therefore the standard deviation is the square root of the variance, right? Or the variance is the standard deviation squared, right? So that's the connection between the two. Okay, so in higher level statistics, I'll make a note of that here. In higher level statistics, which I don't think any of you have to worry too much about, but just be aware, right? We're not going to go down that road for us because what happens when you square a value? When you square a value, you lose information such as a negative. Now you can't have a negative standard deviation, but it becomes kind of harder to interpret, right? Because you've got the variance, and if you have a squared value, it becomes this parabola, and it just kind of inflates the standard deviation. So it's just easier to deal with the standard deviation for when we're just beginning. Okay, that's not something you have to worry about, but just be aware that that could change if you go into higher level statistics. So in higher level statistics, many calculations involve the variance but we will focus on the standard deviation for simplicity. But we will focus on the standard deviation, and I'll bump this up just a little bit, just a smidge, so that I can find it, or just have one more line. Focus on the standard deviation for simplicity. And that's pretty common, you know, in a first course of statistics, that's really common that we do that. Okay, good. So focusing on the standard deviation, what do we think it is? Okay, we know it's a measure of spread. And honestly, as long as you know that it's a measure of spread, so the larger the standard deviation is, the larger the spread is of the data, right? That's a great start. And I'm happy with if that's all you kind of get from the standard deviation from today. But the standard deviation measures how far each point, so each data point, is from the mean. It does a little bit more than that, okay, as we'll see from the formula, but essentially that's what it's doing. Okay, so the standard deviation, is a measure of spread. Oops, helps if I spell correctly. Or even write correctly. Let me start over there. Is a measure of spread. Specifically, it takes into account the distance of each point from the mean. Okay. Specifically, it takes into account the distance from each, or the distance of each data point, I think I want to say here. The distance of each data point from the mean. Now, in the notes, okay, I've got I'll grab this whole blurb here. So I've been very careful not to say that it just does the calculation of the distance. It takes it into account, okay? And so a little bit different, because here, as you can see, the formulas are a little bit more complicated than that, okay? And so there are lots of formulas. I'm introducing two formulas, right? So there are two common formulas that we use to calculate the standard deviation. And I'm gonna introduce both, okay? I find that the first one kind of helps us visualize what it is, what it's doing. But in terms of calculating the standard deviation by hand, which we're not actually going to do, it's not something that I want you to do. We're going to use software, okay? But if you had to find the standard deviation by hand for a data set, then I would probably recommend using the second equation, because it's a little bit easier to deal with. Okay, so the first equation is nice because it emphasizes that the standard deviation considers the distance between each data point and the mean. But the second equation requires less work. Okay, both of these look a little scary probably, and that's okay. We're gonna work through them a little bit. Not too much, because we have software, okay? But let's break down this first equation, okay? So if we have S is, and it kind of generated in a weird way, the sum of the x's minus x bar squared divided by n minus 1. Let me clean that up. There. That's the same, right? If I'm multiplying a fraction by a fraction, technically, I can just scoot them over. I don't know why it's off to the side there, but it is. Anyways, I change my notation over time, I guess, too. So this is the same as the first one here. Whee! Like that. Okay. And so what would we have to do? So if we have to sit down and we have to break down this formula, well, step number one would be to find the mean, right? Find the mean of this data, so of all these x's, okay? So step number one, find the mean. If you're doing it by hand, you'll probably end up rounding that value to some number of decimal places. I would say no less than 2 decimal places. I try to keep 4. In fact, I usually end up keeping all my values. If you've got a calculator that you like, it probably has a store function, which means you can carry all your decimal places. But if you're rounding, just remember that that's going to change the value compared to what R would give you, for example, or what the Excel would give you, for example. Okay, and so step number one is find the mean. And then step number 2, if we kind of start inside the main brackets here, so you want to go kind of as deep into the shell as you can. It's hard because we all, in this class especially, everyone comes from different math backgrounds. So maybe this feels easy and that's great, or maybe this feels really hard, but don't worry too much about it, right? We just have to kind of talk about it, but I'm not gonna make you do it for marks, okay? I might make you do it on an assignment or something, but because I'm just realizing there might be an assignment question where you have to do it by hand, but otherwise you can just use software. Okay, so the next step working within those brackets is from each value of X, right? So now you've got your data set, so that list of all the X's, the GDP data, for example. So from each of those values, you would make a new column of each of the values minus the mean. Now the mean is the same for all those values, of course, right? And so you're just subtracting a number from each of them, right? And so it's taking into account the distance from each of each value from the mean. So then step 2, create a new column where you subtract the mean from each data point. Okay. The next thing you're gonna do, so now you have your column of your data, you've got a column where you have the data, each data point minus the mean, whatever the mean is, okay? Then you're gonna square each of those values. What does that do? Well, if a value of X is below the mean, which would happen, right? Because the mean should be roughly in the center or depending on the distribution, but there are going to be some values that are below the mean and some that are above. But if you have a value below the mean, you're going to get a negative value, right? That doesn't work because in the end, we can't take the square root of a negative number. So we need to get away from that. How do we deal with that? Well, we can square values, right? Make them positive, and it inflates it a little bit, but that's okay because we're going to take the square root later. Okay, and so step number 3 and just to have it not so messy, I'll ditch those arrows because otherwise there would be like 3 more arrows. That's not fun. So step number 3 is to make a new column with each value in the previous column squared, right? This eliminates any negative values. Or this makes all values positive, right? And then we saw the summation notation, fun to say, fun to do. We saw the summation notation before for the average of the x's, right? Where we just have to add up whatever is contained in the summation. So in this case, all of this is contained in the summation. So your next step is going to be to add them all up, right? So now you're going to have a third column, I guess, where you're going to be able to add up all those values, and that would be the sum. Okay, so step number 4, maybe I'll say sum, which really is just add, sum the values in from step 3. Sum the values from step number 3. Okay, that value is going to be the numerator in your square root. Numerator, remember, numerator is numero uno, so it's on top, right? And then the denominator is on the bottom in a fraction. And just a little bit of refresher for fractions terminology. And then we're going to divide by n minus 1. This is very similar now to just an average, right? We kind of do the same stuff. We're kind of a one-trick pony here. We do divide by n minus 1 because it gives us a better approximation. We're not going to go into why. Just take it as because I said so, right? And it's because it's a sample standard deviation and it just gives us a better approximation. But we're not going to worry about why it's n minus 1. Okay, so step 5. Divide the value from step number 4 by n minus 1. Okay, and then finally, running out of colors here, finally, let's do maybe a teal. Find the standard deviation by taking the square root of the value from step number 5. So step number 6, find the standard deviation by taking the square root of the value from step number 5. Okay. There are a number of reasons why our value would be different in our hand calculation versus an R output, right? Because we might be rounding the mean, right? We might even, when we divide by n minus 1, it might give us a long decimal, and so we might round that value. And then when we take the square root of that, even if we've rounded the value from step 5, we might end up having to round the value of the square root as well. And so there are kind of multiple points where we might be rounding, and that would yield a different result than software, which keeps all our values. Okay, so just as a note, if calculating by hand, if calculating the standard deviation by hand, the value might be different from software output. The value might be slightly different from software output due to rounding, right? So depending on how many times you've ended up rounding, right, that would affect your results, right? Software does no rounding, right? Software, and I say software, in general, I'm gonna mean R, but it could be Excel or SPSS or SAS or whatever. So software will keep all decimal places. Okay. So that's how you would do the calculation by hand. Notice that I'm not actually going to do it. I think in the notes it has it all printed out, but and I'm not going to go into too much detail, but why is this second one easier to deal with, right? If you look at the formula here, right? First thing you would do to find this value is you would make a new column of each of your x's squared. Add those all up, and that would be what's in this bracket. And then you would have your average, which you would square, multiply by n, subtract from that x's squared sum, then divide by n minus 1, then take the square root, and then it's very similar, right? So I find that that's a little bit easier, but that's why I wanted to walk you through that first one. So notice you only need one, so just be comfortable with one of these calculations. And what I would encourage you to do is take that GDP data set and just try it with both formulas and make sure that you get the same value. Depending on your rounding, you have to be a little bit flexible, but it shouldn't make a huge difference. Okay, and then I'm going to find it using R and show you how to do that. So then you'll have something to compare it to. Okay, so just make sure you're comfortable working with that. Okay, so before I show you how to do it in R, the last thing I want to introduce is the interquartile range. Okay, so remember, so for a normal distribution, we use the standard deviation. For a non-normal distribution, we're going to use the interquartile range. For a non-normal distribution, we use the interquartile range as the appropriate measure of spread. Okay. Now the interquartile range is almost always abbreviated IQR, because interquartile range, that's really kind of long to say and write. Okay, so IQR, the interquartile range is, if you break it down, it is inter means between the quartiles. What are the quartiles? What do you think the quartiles are? Well, we've already seen the median, which splits our data in half. So our quartiles would split our data into quarters. Fair enough. Okay, and so we're going to have these quartiles or quarters, and there's some range between them, and that's the interquartile range. Okay, and so we can split our data into quarters, and these values will be our quartiles. And these values will be our first and third quartiles. Q1 and Q3 is typically how we denote them. So Q subscript 1 and Q subscript 3 is typically how we write those. Now, if you think about it, the median splits your data in half. And so the median is the second quartile, 2 quarters, 2 quarters. So here, note, the median is Q2, right? The second quartile. Okay. So once you have your median, then you're going to focus on the lower half of the data and the upper half of the data, and you're essentially going to find the median based off of the lower half and the upper half. Okay, so the quartiles are basically the medians of the lower half and the upper half of the data respectively, are essentially the medians of the lower and upper half of the data, or upper halves of the data. So we use the same method as we used to find the median. So we use the same method that we used to find the median. Okay. The only difference is that if you have landed on one value and that value is the median, you don't include it in finding your quartiles. Whereas if you have taken the average of two values, then the median is in the middle of those two values, then you can use those values on either side. If the quartiles are like quadrants, not quite, because quadrants typically refers to kind of quadrant one on a plot, right, on an XY grid. So not quite, but depends on your definition of quadrant. Okay. And then your interquartile range, because I forgot to introduce this, is Q3 minus Q1, the distance between the two, Q3 and Q1. Okay. Yeah, I'm just about to. So there are two scenarios, okay? And so to find the quartiles, there are two scenarios. Okay. So the first one, let me go back to, let's use this one here. Copy. I'm gonna cheat here. And maybe here, let me bump this down just a little bit more so I can outline the scenarios. Scenario one, the median is between two values. The median is between two values. Like it is here, okay? In this case, we can use those two values because the median is here. So then if I want to find the first quartile, which is essentially finding the median of the lower half of the data, right? If I'm breaking this into quarters, not just in half, but into quarters now, and that's what we're doing, then I can start my count from 4.6 and 4.7 if I'm going up. Okay, and so here, if the median is between two values, we use the values. We use the values on either side to find the quartiles. That's true for the next scenario as well, where we've landed on a value, but we still use the values on either side of the median, which kind of looks a little different. Okay, and so here to find the first quartile, boom, 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 boom. Okay, so what it happens is my Q1 is 3.9 plus 4.1 divided by 2. I'm just going to confirm, I think it's 4, but 3.9 plus 4.1, it is 4. Okay. So then I was able to use the 4.6 because the median is actually here in the middle. Now for Q3, I can do the same thing and I can start at 4.7. 1, 2. And maybe I'll go up this time because I totally ran out of space here, but Q3 is 5.4 plus 6.2 divided by 2. 5.4 plus 6.2 divided by 2 puts me at 5.8. Okay. Now, what about scenario 2? The median is one of the values in our data set. The median is one of the values. So for example, what's going to change here, if I paste this, and this is no longer going to be our median here, because what I'm going to do is I'm going to add maybe 21 here. And I'm making it huge on purpose. Okay. So then these won't be my boop, boop, boops anymore. Right now I've got a different number of data points. Right now I have 13 data points, but I would go boom, 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 oh, boom, 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 boom. I'll just count to make sure that I did that correctly. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Phew. So then the median here is just the 4.7. Since the median has also, since 4.7 has already been used, we cannot use it to find our quartiles. Okay. So here, since 4.7 has already been used, we may not use it to find our quartiles. That's the same thing, right? But it for some reason, it gets a little confusing. So we use the values on either side of the median. Let me add that here. So on either side of the median to find the quartiles. That's the same rule, but now that we've used the value, now I use the values on either side. Okay, and so then my boom, 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 boom. Q1 looks the same, and here, boom, 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 boom. Q3 changed a little bit. So Q1 is 3.9 plus 4.1 divided by 2, which is 4. And Q3 is 6.2 plus 7.3 divided by 2. Okay. 6.2 plus 7.3 divided by 2 is 6.75. Yeah. Okay. And I guess for each of these, I should have found the interquartile range. So let's go back to scenario 1, where the interquartile range, I kind of ran out of space here, is Q3 minus Q1. Bump that up just a smidge here. So the interquartile range is 5.8 minus 4, which is 1.8. I don't like to write my equal signs across the page because I don't like to see it, and I don't want you to do it either, but well, I ran out of space. So the interquartile range here is Q3 minus Q1, which in this case is 6.75 minus 4. Oops, it's not the average, which is 2.75. Hopefully that helped showing the quartiles. Okay. One thing to note, I was hoping to show you guys some more R code today, but I'll save it for tomorrow. And what you'll find is that sometimes software will give slightly different values because it has a more sophisticated way of finding the quartiles. For example, I think once we check out software, I think it's gonna say that the first quartile is 4.1, and that's because it does kind of a weighting thing. It looks at the other values, and it's way fancier than what we would do by hand. So this is how I want you to find these values by hand. And that's what I'm expecting you to do on the assignments. But you can always check with software, but just be aware that it is going to be a little bit, it's going to do kind of a weighted thing, okay, kind of a weighted average. Okay, so just a note, we can use software to find these quartiles. We can use software to find the quartiles. But most are using a more sophisticated method than what we have. And so some values will be slightly different. But most use a more sophisticated method so you should expect your values to be slightly different. Your values to be slightly different, right? I only say that because I don't want you to freak out and try to figure out why your values are different. If you're working on a problem, just expect that they might be slightly different, but they should be in the same realm. Okay, so for tomorrow, the video that I post will have, we'll work through just how to do these in R, and then you'll be able to kind of work through it at your own pace, and I think that's good. So if you have any questions, let me know. Otherwise, I'll see you just on Zoom on Tuesday, and I hope you have a great weekend. Stop this recording here.